the share screen for the textbook. Very good. Transfer of thermal energy. This is a relatively easy in terms of concept, but questions are typically application. So a lot of times students are unable to decipher which method are they looking at in terms of conduction, convection, radiation. So today I'll be going through a little bit more on the foundational concept that's going to help you to determine how to go about applying the conduction, convection, radiation. Okay, so we're at chapter 8 now. Okay, we're going to look at the 8.1. I'm not sure how many of you really spend time looking at it, but 8.1 is actually a very, very important part. Okay, without 8.1, the rest of it actually is very hard to apply. So for 8.1, what you're going to learn is that you're going to show and understand the temperature and apply the concept to solve problems. Now, okay, why does the object okay, you can go and read up, but I want you to understand this. Okay, thermal energy always flows from a region of lower temperature. Okay, when there's a difference in temperature. So before you jump into any questions regarding heating or regarding the transfer of heat, you must always check. Okay, always must check. So this is the part. Before you start to think about conduction, convection, radiation, you must always check how or what direction is the heat being transferred. And how do you check? Okay, it's really by looking at this. So the thermal energy will always be transferred from higher temperature to lower temperature. So all you need is just to check which one is the higher temperature, which one is the lower temperature, and then from there you can determine what is the direction in which the heat is being transferred. Okay, so I'm not even talking about conduction, convection, radiation. I'm just talking about what direction is the heat gonna flow. Okay, direction that the heat is flowing. Okay, or where does it start from? Where does it go to? Then you will be able to apply subsequently conduction, convection, or diffusion. Which of this method is the one that is working? Okay, so this is the first part here. Really key concept: thermal energy always flows from a region of higher temperature to lower temperature. Okay, so must always decipher where the energy flows. Then really the next part comes in is talking about the three different methods in this chapter here. So we got conduction, convection, radiation. So conduction. Okay, conduction is the transfer of thermal energy. Obviously, it's a transfer of thermal energy because it's one of the process in which heat is transferred. Okay, through a medium without any flow of the medium. People always like, what do you mean by that? Okay, I want to like this. Okay, so now a bit faster. Now means this is being heated up. Okay, they will remain here. They will not. This movement is not possible. This flow is not possible. Okay, in conduction. So in conduction, we really is talking about how the heat is being transferred without those. Okay, so then the question: if they don't move from one place to another, how do they exactly pass the energy? Okay. Conduction work. Okay, how does conduction work? So what happens is that when there's heat here, so the fire is when there's a fire over here, So the particles here over at this region will get heated up. Heated. Okay, when they get heated, they'll vibrate vigorously about their fixed position. So when they vibrate more vigorously, okay, because there are neighboring particles around them, what would happen? They will collide. Now, in this collision, what actually is happening? During this collision, the kinetic energy is actually being transferred to the neighboring particles. Okay, and because the kinetic energy is being transferred, it will vibrate more vigorously. So I repeat this part again. When you heat up, these particles vibrate more vigorously. And because there are neighboring particles around them, they will collide into them. In this collision, okay, they will actually pass the kinetic energy to the neighboring particles and cause them to vibrate even faster, to vibrate faster. And this process carries on, okay, carries on all the way until this part also becomes hot. So you can see here, okay, heat up, vibrate vigorously, fixed position, collide, making them vibrate more vigorously. And why is it so? Because the Ke is being transferred to the neighboring particles. Okay, now, so this process will carry on. Okay, so this is a process of conduction for non-metals. Okay, it's about the particles colliding and passing the energy from one to the other, to the other, to the other, until all the way to the end. So that's how conduction works. So this process, okay, you will see that it's termed as atomic vibration, or sometimes another word that they will use is called molecular vibration. So this is the most basic mode for conduction. Okay. Now we know this is the most basic way conduction occurs, but we also know that metals are good conductors of heat. Now, what makes metal better? Isn't all conduction the same about energy being transferred from one end to the other, about the particles colliding? So why metals have this little difference of making them such a good conductor of heat? Okay, if you read here, this is the part that tells you why. So as you heat up, you see that actually there's still molecular vibration. So in metals, there is also still this concept of the molecular vibration. Okay, however, there's one extra mechanism. Okay, there's another much faster mechanism that's helping with the heat transfer, and we call it the free electron diffusion. So for metals, there's not only molecular vibration, but there's also a very fast method to pass the heat along the metal rod itself, which is free electron diffusion. Okay, so you can read up here. Okay, general idea is that when you heat up, it's not only about the particles gaining heat, moving faster, but the free electrons will also gain kinetic energy. And because they move faster, they're able to go from one end to the other end faster. And as they collide into the neighboring electrons, neighboring particles, they actually transfer the kinetic energy to them. And this energy will cause the particles to vibrate faster, which then speeds up the process and make the heat being passed down from one end to the other end. Okay, so the difference really between non-metal and metals is that metals have this extra mechanism, free electron diffusion, and hence, because metals have this extra, okay, I use the word they have this extra mechanism. I always say that non-metals are generally what? Poor conductor of heat. Okay, they call poor conductor of heat. So yeah, poor conductor of heat. It actually means that they transfer heat through. They transfer heat through. Okay, depending on whether you're comparing with another material or you're just looking at it itself. Always deem them as comparing or just looking at the items or looking at the object itself. So this important because that's how you're required also to write answers when you're describing how good a material is when it comes to conduction. When it comes to conduction, okay. Now then the question is, do I need to memorize these descriptions? Okay, so far I haven't really seen people being asked to describe free electron diffusion, but okay, there are exam questions being asked, okay, regarding molecular vibration. So you may need to memorize all this, but actually if you understand the concept of it, you need not memorize it. You can actually explain it. Just take note of the keywords such as vibrating, such as colliding, such as kinetic energy. Okay, so collide, vibrate. Okay, so these are the few keywords you must take note if you are describing it. Okay. Does liquid and gas conduct heat? The answer is yes. Okay. So thermal energy can be conducted from a hotter region in liquid and gases also. Okay, but why not efficient? We learn in the kinetic model of matter is that the particles in liquid and gases are called solid. The particles are very closely packed. Okay, whereas for liquid and gases, liquid is closely packed, gases are very far apart. Okay, so when they are far apart, what actually happens is that they collide less frequently. If they collide less frequently, are they able to pass energy quicker? Of course not lah. They actually pass it down slower. Okay, so key idea, not efficient because they are not as close compared to solid. Therefore, collision is less frequent. Okay, and hence the transfer of energy is slower. Okay, so do take note, liquids and gases are poor conductor. Solids can be classified as good or poor conductor. I say again, liquid, gas, there's actually two. It can be non-metal. So if it's non-metal, it's a poor conductor. If it's a metal, whenever you talk about conduction, whether they're good or just want to look at this one a bit. Okay, so which is a poorer conductor of heat, water, or air? Answer is air. Air is a poorer conductor. Based on this logic about the particles being closer together or not, air, the particles are very far apart. So the chance of collision is even lower. Therefore, if you ask me, compared and air, water is a better conductor heat than air. But do take note, although water is a better conductor than air, both water and air, because they are liquid and liquid and gas, they are considered as poor. Anyway, do read through this experiment. Okay, this one is actually quite an interesting one. It has come out before in primary school. Or secondary school, will it come out? Maybe, maybe not. But do take note, this one actually help this experiment actually help you to consolidate your learning regarding conduction and understand the idea between good conductors and poor conductors. Okay, so next up. Okay, so as a general idea, what did we learn for here? Conduction is a transfer of thermal without any flow in the medium. Okay, transfer without any flow. It can occur in two different ways: the vibration of particles, generally for metals and non-metals, and free electron diffusion for metals only. And then when we talk about whether good or poor conductor, liquid and gases confirm poor conductor. Solids can be good, can be poor, depending on whether they're metals or non-metals. Right, so 1, 2, 3, all covered. Now, okay, this part here, 8.3, we're just going to describe how convection occurs, but convection actually occurs because of the key idea, density changes. So if there is no density changes, actually you can't have any convection. So let's look at this. Okay, definition. Convection is transfer of thermal energy by means of current with and what are fluids? Liquid gases. So can convection occur in solids? Answer is no. Okay, so you can only use convection for liquids or gases. Okay, that's how. So solids cannot transfer heat via convection. Okay, so I say again, solids cannot transfer heat via convection. Convection transfer thermal energy by means of in a liquid. So this is a little experiment you can read through. But in actual fact, right, the conclusion is typically the explanation that the teachers are looking out for, or what the question is looking out for whenever you're answering questions regarding convection. So this is actually a very long explanation. There's also another one. Okay, so if you look at this whole thing here, this part, the discussion here, is also the explanation of what is happening and how to go about describing. Now, there is a general shortcut in the way how you're going to explain it, whether it's going to be heating or cooling. Okay, there's a few different ways to go about doing it. So I'll just maybe use the space over here to just write down, when you talk about convection, how should the description look like? So in terms of heating, okay, so I want to transfer heat. Okay, I want to transfer heat via convection. So typically can be liquid or gas. So I just say when the substance is heated. Okay, when the substance is heated, so this is the heating part. What actually happens? It expands. Okay, become less dense. And rises. So you realize there are a few points here. One is you must talk about, because it's heating, right? So talk about substance being heated. Expand. Expand means that the volume increase. When the volume increase but the mass stays the same, the substance become less dense. And because the substance become less dense, it will rise. Okay, so the substance nearer to the heating source will get heated up, expands, become less dense, and rises. This is the first part to the answer, typically when you do any heating explanation. The second part is the cooler substance. Okay, normally the cooler substance is at the top. The cooler substance at the top, is denser, hence it will sink. So key idea here, cooler, denser, sink. Now, once you have this idea that the heated substance will rise, the cooler substance will sink, what is actually happening is that you are setting up what we call this little cycle here. This is called the hence. This process repeats. Sorry, not hence. This process will repeat. To set up a convection current. So do take note, this is a very standard answer. You need to adapt it definitely to the question itself. Okay, so normally when you talk about adapting this answer, it's really about describing the substance. Okay, so don't just write this generic answer here. Learn to adapt it to the question that's being asked. Okay, now, of course, if there's a heating part, sometimes the substance can be cooled. When the substance is cooled down, it can also cause convection current. So this is about cooling. Okay, so I'm going to write down here now. So when substance is cooled, okay, tracks denser, right? So when substance is cooled, it contracts, becomes denser, and sinks. Warmer, the hotter substance, Okay, the hotter and the warmer substance at the bottom uh, is less dense, hence it will rise. Okay, the third part to set up a convection current. The last sentence is the same, the last point. So key is the front part, how you're going to go about phrasing it. So cool, contract, denser, sink. That's in the first bullet point. Second bullet point, okay, so the warmer substance, which is less dense, will rise. So last part, set up convection current. So these are the two typical ways you can use to explain your convection currents. Okay, and you can see this pattern of explanation. So yeah, you can see this pattern of explanation in all these parts over here. Okay, so as I mentioned, which is seen over here, convection only occurs in fluids. They do not occur in solids. Okay, key idea because there is a bulk movement of the fluid. Okay, solids, you don't have that kind of movement. The particles can't fix position. So for convection, if you know how to describe it, or you know how to draw, sink in. I just want to draw the convection of how it will roughly look. So this one over here, where there's two. Okay, let's go on to the last part, which is radiation. Okay, now, so before we jump into radiation, I think this is a good read. The sun emits EM waves. We all know what EM waves are, right? So there's a song that goes with it. I'm not going to sing it now, but EM waves is a whole spectrum. Right? One of the type that the sun emits is infrared radiation, and this makes us feel warm. And this is the radiation that we are typically talking about. So whenever you talk about radiation, okay, radiation in terms of heat transfer, we are looking at the transfer of heat in the form of EM waves such as infrared radiation, okay, without the aid of medium. That means I don't need a medium for radiation to occur. I don't need a material. I don't need any substance. Okay, this also means that radiation vacuum. Okay, vacuum means that there's no substance in between. Right? So, unlike conduction, convection, radiation does not require a medium for energy transfer. It can vacuum. So this is quite important here because typically heat transfer cannot occur. Okay, or many things are stopped because of vacuum. But radiation actually can travel through vacuum. Okay, it doesn't need a medium. So radiation can take place in vacuum. That's a key point. Okay, so this experiment, go and take a look. Okay, I will tell you, you will see this kind of experiment in your TYS and stuff. Okay, so you must be able to differentiate and understand what is it about. But do take note. Just now you saw emission of infrared radiation. This is absorption of infrared radiation. What it means is that when you talk about transferring of heat, you can either emit radiation or emit heat through radiation, or you can absorb heat through radiation. There's both ways. You can go and read out a bit more. I'm not going to go through this experiment. But, okay, what I need to know is this. Before you even jump into emission or absorption, okay, which one is it? Now, do take note. Whenever you're talking about description of radiation, you can't say like good emitter and good absorber of radiation. You don't write both. You only write one of them because it must be specific to the scenario. So question is, when should we talk about emission? When should we talk about absorption? So key idea here, when we talk about emission, when I talk about absorption. So if I got object A, object B. Okay? Now, key idea, how do I know which is emitting, which is absorbing in general? Right? It's really about the temperature. If this is 50 degrees Celsius, if this is 20 degrees Celsius, what's going to happen is, because this guy compared to this guy, object A compared to object B, object A is of higher temperature, so it will emit heat via radiation towards B. And because B is of a lower temperature, so B will be the absorber of radiation. So that's why you can't jump into radiation talking about emission or absorption straight away. It goes back to 8.1, as I mentioned. You must always figure out whether the substance is absorbing or emitting heat. Okay. So now, okay. So once I will determine whether it's absorption or emission, the rest of it comes in quite nicely, lah. Okay. So first thing, how can I speed it up? How can I slow it down? So first one is on the color and texture. So dull, black, and rough surface. Okay, you can add the rough in lah. Dull, black, rough surface are better emitters and absorbers. Okay, so you realize they wrote both here. However, depending on question, okay, you must be able to adjust it accordingly. So dull, black, rough are better emitter and absorber compared to shiny, silver, and smooth surfaces. Okay. So typically I'll group these three together. So do note that the color and texture of surface does affect radiation. Next one, surface temperature. Okay, this one is quite intuitive. The higher the temperature of a substance relative to the surrounding temperature, the higher the rate of emission. So if my temperature is higher, I will emit more heat. Okay, that's what the idea is here. And last one, surface area. The more surface area being exposed, the faster the emission of radiation or the faster the absorption of radiation. So surface area, how can I increase it? Okay, if you see in questions, okay, what are some of the things that utilizes surface area? So radiators in car, okay, they have this concept called fins. Okay, the fins actually increases surface area. Okay, the other one is you will see plates. Okay, flat plates. Okay, connected to tubes and stuff to allow for this kind of heat transfer. So do take note, surface area, the larger the surface area, okay, the absorption and emission of the radiation will also be at a higher rate. So three main factors: color and texture, surface temperature, and lastly, surface area. You must know these three factors on how it affects the rate of radiation, okay, because it's commonly tested, so you must be aware of it. But in real life, in terms of its application, there's quite a fair bit lah. Okay, so you can go and think about it. Okay, you can ask if you want later on. Done with radiation, so it is the transfer of thermal energy in the form of infrared radiation. Okay, it is emitted from the surface of all bodies. It does not require a medium, so it can be done in vacuum. Okay, dull, black, and rough surfaces are better absorber and emitter than shiny, silver, and smooth surfaces. Okay, these are the three factors that affect the rate of radiation. Now, we have gone through conduction, convection, and radiation. Now we're going to look at the application, because you know that in the exams, in the tests, then it's not going to be so simple as just ask you how to describe radiation, convection, and stuff. They like to always show you an experiment, then ask you some questions to apply your knowledge on conduction, convection, and radiation. So this is where the examples come in very handily. Okay, so good conductors of heat, poor conductors of heat. Okay, you will be able to use them both in daily life. Now, so what is happening is that cooking utensils, all these surfaces, okay, they are all metals. Right? Because why? You want the heat to be transferred through the pan to the food quickly. So that's why, because I want the thermal energy to transfer, we use good conductor of heat. But what you realize about the handle, all the handles over here, they're all poor conductors. Because imagine you want to hold on to the handles, but yet it is a good conductor. So once it's being heated up, the heat quickly transfers to your hands, it becomes very hot. So what to do is that they will actually attach poor conductors to the points where you'll be touching, so that heat will not be conducted quickly through your hand. Soldering iron rods, the tip, okay, so it's to make sure that the heat is being transferred efficiently to the tip, so that you can melt the solder. Heat exchanger, okay, this is another interesting one. Okay, hot dirty water is here. What is happening is that the tube is made of copper. Okay, so this whole tube here is made of copper. So copper is a metal, it's a good conductor of heat. So what's happening is that the hot dirty water, okay, will be conducted quickly through the copper tube to the outside cooler water. So as it passes through, the copper will quickly take the heat from the dirty water, hot dirty water, and pass it to the cold clean water. So conduct the heat quickly to the water, cold clean water. So you can see once it's out, this dirty water is cooled down. Right, so the copper tube, being a good conductor of heat, allows for the heat to be transferred quickly from the internal to the external side. Now, poor conductors of heat, you can actually use it, okay, as a way to apply it. So as I mentioned, handles, table mats, okay, to make sure that you don't burn the tables. The other one is woolen clothes, okay, woolen clothes or cotton, air. So the key idea is not that the cotton is good for, it is good to keep you warm. Actually, the key idea is the cotton actually is very fluffy, it traps air. And the air, you know, is a poor conductor of heat, hence it keeps people warm. It prevents people from losing heat quickly. Another one is called the double glaze window. So you can trap air in between. So solid with a layer of gas in between another solid. So because you know gas is a poor conductor of heat, hence heat transfer inside the house or to outside the house is actually slowed down. Okay. For some of the other situation, sometimes if you read carefully in questions, they might not use air. Okay, they might actually sometimes even say I put vacuum. Now, if I put vacuum in between these two glasses, if I use vacuum instead of air, so what's going to happen is because you know conduction and convection cannot occur in vacuum. So by putting vacuum in between the two glass, what's going to happen is that you will stop conduction and convection from happening, okay, which is quite good. Okay, which is quite good. Okay, next, in terms of convection. Okay, now if I want to heat up a substance, you realize the heating supply is always at the bottom. Why? Because when you heat up a substance, the heated substance will become less dense and it will rise. So if you put it at the bottom, the hotter substance will always go up, the cooler substance can always come down, and it will form a convection current. So heating elements or things that you want to put the place to heat things up, you always keep it at the bottom to allow for convection to occur well. Okay, you want to cool things down, okay, you will typically put the cooler system at the top. So that's why aircon is always placed at the top. Okay, household hot water system. I'm not going to go through this because it's really quite a lot of points here. Do take time to read through this because this has come out in some, I think some of the prelim questions on even TYS, they have a segment, a certain part talking about it. So this one, do take time to read through. I think it's quite easily understood. If you got any questions, of course, you can feel free to ask your teachers about this. My suggestion is go and read through this. Quite an interesting system where they actually is in real life and also is a very good application in terms of convection. The air conditioner, as I mentioned, is always placed at the top, right? Because if I cool the cool air will sink. The warmer air will come up, and the aircon will cool it down again, so it will form a convection current. So key idea here is whether when you want to let convection be efficient, okay, if you want convection to efficiently transfer heat, or convection to efficiently transfer, okay, whether is it cooling down or heating up, focus. Heating elements should be at the bottom. Cooler cooling elements should be at the top. Okay, so take note of this. Okay, radiation. Okay, so this one is about the glass house. So this longer, shorter wavelength, this one you realize it feels a bit like jog, okay? If you look at many of the questions, we don't really talk about longer and shorter wavelength. Right? Typically, radiation application, we will look at the color, okay? We will look at color of objects. Right? So if I want to have something to emit heat through radiation quickly, I'll make sure that it's black, I'll make sure that it is dull, and I'll make sure that it is rough. That will help me to emit heat quickly. But if I also want to absorb radiation quickly, I'll also use the same kind of surface. So surfaces actually is the color of it, the texture of it, is a common application of how radiation is being used in real life. Okay. Now, vacuum flask very long never come out already, okay, but it's a commonly used item now. So I want to run through each of these items step by step. So vacuum flask looks like this. You have a cap, another cap inside. Then you realize that there's this cork around it. There's a between the silver line walls. So all these little things actually makes a difference to the function of the vacuum flask from the plastic stopper. Plastic, key idea, poor conductor of heat. Because it's poor conductor, it reduces heat transfer by conduction. And because the air inside cannot flow out, that's why I also reduce heat via convection. And last one, because the air cannot escape, there's also no evaporation. So key idea, plastic stopper, not only because it's a poor conductor of heat due to this material, because of the way how the thing is designed there, it actually reduces heat via quite a fair bit of methods. Next thing, trapped air over here. Right? Once again, air is a poor conductor, so it ensures that the liquid here do not conduct heat quickly to the plastic stopper. Okay, so you add another layer. So plastic here plus air here. So you can imagine how good it is in trying to reduce the heat transfer from the hot liquid out. Next, vacuum. So this white space over here is actually filled with vacuum. Well, I cannot say it contains vacuum. So when you have vacuum, what actually you are doing is preventing conduction and convection. Because conduction and convection requires a medium for heat transfer. But because I got vacuum over here, I am preventing conduction and convection from the hot liquid through the walls. Okay, so I am preventing it. But conduction and convection still can occur here. Okay, this part can still convect, just slower. This part, okay, is no conduction, no convection because of the idea of vacuum. Now, so if cannot conduct, cannot convect, okay, no conduction occurring, no convection occurring at this part here, it is still not fully successful yet, because remember there are three ways heat can be transferred: conduction, convection, and radiation. So radiation is still another factor we need to consider. So how can we slow down radiation? Well, you realize the surface that's smooth, okay, and shiny. What is going to happen is that it's a poor absorber of radiation. So the heat transfer minimized. So this is a in this vacuum flask. A quite interesting one, because many of these applications talk about conduction, convection, radiation all at the you need to be able to apply conduction, convection, radiation, talking about the kind of heat transfer, whether you want to maximize it or you want to minimize it. Okay, so it's not just about the theory of what conduction, convection, radiation is, but it's how you can apply it to the things around you. Okay, so coming to the end, let's look at the map it here. So transfer of thermal energy, three main process. But before we even talk about the transfer of thermal energy, you must always remember it's always from a higher temperature to a lower temperature. So this is the base you must always establish before you even jump to conduction, convection, or radiation. Conduction, non-metal by vibration of particles, metals got vibration, and free electron diffusion. It needs a medium. Convection is only for fluids by means of convection current. Okay, and why convection current form is because of the change in density. Once again, it needs a medium. Okay, because particles vibrating for conduction, convection is about the particles moving. The last one is radiation, is a infrared radiation. Do take note, I do not, it does not require a medium for this kind of heat transfer. And these three are actually applied in your daily appliances whenever I talk about heat transfer. Okay, so actually that's all for chapter 8. To really reinforce your understanding, okay, you can actually go and look at your TYS questions for this chapter. Okay, you realize that they are quite standard. The answering technique is actually quite similar. Most people are not able to do it correctly is because they always forget this point. So remember, before you jump into any of this conduction, convection, radiation, always ask yourself, how? What is the direction of heat transfer? Okay, so that's all for this chapter. Very good timing. Within 40 minutes, things are done. Yay! Okay, now let me stop sharing. Stop the recording.